This presentation is delivered by the Stanford Center for Professional Development.
Okay, I guess we're on. Welcome to 364A, which is Convex Optimization 1. Unfortunately, I have to start class by apologizing. If you're watching this, not in real time, I guess you'd say, I don't know how you describe that. If you're watching this at the scheduled time of the class, then you'll notice that I'm not there. That's because I'm in India. It gets very, you can actually get very confused doing this. There's actually one more confusing thing than this, and that's when you tape ahead a class before that actually goes after a class you haven't given yet. That gets very complicated. Well, we're not going to go there. Let's move on. So I'm sorry to miss the first day of the class. As I said, I'm in India, or will be, or depending on where the time reference is. That's very tacky. I've never done it before, so this is a first. Actually, we're going to make a lot of firsts today. I believe we may be making SCPD history because we're taping ahead this lecture not only the quarter before, but the year before, calendar year before anyway. So a lot of people are very excited about this. If this works out well, who knows where this is going to go. So I could teach like all of my spring quarter class, say the last few weeks of winter quarter. Or anyway, we don't know what, we'll just see how this works. So we're possibly making tape ahead history here. Okay. Couple things I should say about the class. I mean, other than apologizing for not being present, or for that matter in the country for the first day of it. I'll say just a couple of things, and then we'll actually just get started. For those of you watching this, since you're not going to get to see the audience, and know that I sent out a pitiful plea to come if you're around for the tape ahead. You should know that no, the room is not empty. So anyway, all right. Let me say a little bit about the class. I mean, I think some of it is kind of obvious. We've just barely got the website up and running. We change it every day. But let me say a few things about it. The first of the requirements, there's going to be weekly homework, which if you're interpreting this relative to January 8th, I think the correct statement would be, has already been assigned. If you're interpreting it in real time, it's actually false because we haven't even thought about homework 1, but we will. It'll all be ready to go. So there'll be weekly assignments, and there'll be a take-home final exam, which will be the standard 24-hour take-home exam, the usual format where you get to. It will be non-trivial. You get to do serious work and stuff like that. Okay, and the other requirement for the class, not really a requirement, but there will be maybe almost every homework or something, there'll be minimal MATLAB programming. It's not a big deal, but there'll be MATLAB programming, and that'll also be done using a system called CVX, which you should, if you go to the website, you'll look into and can find out about it. You're actually welcome to sort of install it, read the user guide, like basically now. There's no reason not to. You'll be using it like throughout the year. I'm all confused. The quarter, or next quarter, whatever it is. The quarter in which this class is actually supposed to be. You'll be using it throughout there. So you might as well look at the user guide, install it, see if it works. Not everything in the user guide will make sense until you get to about week 4 of the class, I would say. But there's absolutely no reason you can't start poking around with it now. And it's not a big deal. In fact, when we get to it, I think you'll be, or you should be, extremely grateful for the existence of this stuff, because it actually trivializes the programming that we'll do in the class. Programming is in quotes. That should have been clear from my tone of voice. And the reason is we're talking things like 10 lines and stuff like that, so not a big deal. Okay. Oh, by the way, on that topic, I would say this. If there's anyone, the CVX is based on MATLAB. That's just, well, that's the way it is. If there's anyone actually who wants to try to use like a real language, like for example Python, I will be very happy to support you in that. Actually, is there anyone here who's crazy enough to do this or something? No? Oh, that's sad. We're hoping, actually I can tell you, so the TAs are Young Wong, whom I guess you can't see, and Jacob Mattingly, who's in New Zealand. But when this is played back, will not be in New Zealand. Anyway, Jacob would be very happy to, if at least there's one person who hopes to does all the numerical stuff in Python. So I'll just say that, and then if there is such a, feel free to come forward and let us know. Okay. Only other thing I would say is, something about the prerequisites, and then we'll actually move on to the class. So the prerequisites is basically a working knowledge of linear algebra. So that's something that 263 absolutely clearly that's perfect background. If you did 263, got almost all of it, you're cool and ready to go. If not, I mean, what we mean is a working knowledge. So not the ability to actually know about these things, but actually how you use them in modeling and things like that. So, and the other one is the mathematical sophistication level is going to be a jump up from 263. So 263 is, it's a 200 class. This is a 300 level class, and so the mathematical sophistication is going to jump up. The cool part is the mathematical sophistication jumps up, but actually it's still in some sense a very applied course, in the sense that we're not just going to talk about optimality conditions. You will do, I promise, portfolio optimization. You will do optimal control. You'll do machine learning. And I mean like actually do numerical stuff. And it won't just be stupid programming. It's going to be learning, actually figuring out what's going on. It won't be obvious, and stuff will happen. It'll be good stuff. Okay, so I'm trying to think what else to say before we start in on the class. Maybe I'll just set it in context, how it's different from 263 and stuff like that. That would be a good thing. And then we're just going to start in. So the 263, which is a linear dynamical systems class, I would call that kind of basic material. It's useful in tons of fields. It's very widely used. A lot of people know it. So it's used in economics. It's used in navigation. All of these areas. Control, signal processing is basically all done this way. Communications, a lot of stuff is done this way. And it's a great first look at sort of how these mathematically sophisticated methods actually end up getting used. 364 revisits it, and actually it's quite a bit different in a couple of ways. The first way is you might even just say this is 263 beyond least squares. So in 263, and by the way, in other courses similar to that, so in your first look at statistics, in your first course on statistical signal processing or whatever, it's the same story. Everything is Gaussian, all distributions are Gaussian, all objective and constraints are quadratic and so on. And you do this because there's analytical formulas for it. And then behind the analytical formulas, we have very good computational tools to give computational teeth to the theory. So here, it's going to be way beyond that. We're going to have inequalities. We're going to have all sorts of other interesting norms and other functions. So we're going to see. It turns out it's a much richer class of problems, and these are problems much closer to a lot of real problems. Ones where, well, you can't handle. I mean, you don't have the concept of an inequality in 263 in a linear systems concept. You just don't have that. You have no way to deal with noise with a Laplacian distribution in your first class on statistical estimation, for example. So we're going to look at things like that. It's going to be, it'll be fun. I should also say that the number of people who know this material is relative to 263 material very small. It's probably a couple thousand. That's all. It's growing rapidly, but it's just a couple of thousand. And so that means you're going to move from, material, a lot of the 263 material, a lot of it's kind of from the 60s and 70s. Not a whole lot later, honestly. Maybe, some of it, but it's kind of, it's not stuff that's new. This class, in contrast, you're at the boundary of knowledge, so which makes it fun. So it means who knows? Maybe you'll even push the boundary. Actually, I hope you do, because that's kind of the point of the class. Actually, is to train you to go find your corner of the boundary and start prospecting. Okay, so I can't think of anything generic to say, so maybe we'll just start the rest of we'll actually start the class unless there's any questions about. Yeah.
If you haven't taken 263, is it a big problem? If you do have a working knowledge of linear algebra, but
No problem. What'd you take instead? Something somewhere else?
yeah, somewhere else, not here.
Okay.
But I mean, and I've
Where?
just taken CS2-9 too. So
Oh, you're fine. That's okay. That's no problem. Yeah. Okay. So, oh, I should also say this about the something about the background. I should say, obviously the class is listed in electrical engineering. I'm not actually sure why, but anyway, it seems to be it's a tradition. Last I checked, that's the department I'm in, so it just seemed like a good idea all around. But I should say this: you don't need to know anything about electrical. In fact, we'll talk about lots of applications throughout the quarter. And actually, honestly, probably for half of them, I don't even know what I'm talking about. So, and that will surely happen. You'll be in some field. I'll super duper oversimplify it, and you're welcome to point that out. If the lecture's boring at that point, you can, shake your head and then say, no, that's totally off or whatever, and then, I don't know, we'll all laugh, and I'll continue then. But the point is, I'll talk about circuit design, we'll talk about machine learning, on all of these topics, there'll be people in the class who know more than I do about it, number one, and there'll be a lot of people who don't know anything about it, but if you're one of those latter, don't worry about it, they're just examples. I should say there is one prerequisite, although I don't know what would happen if you didn't have it. That is that I will assume that you know about basic probability estimation and things like that. So that I'm going to assume. Okay. Any more questions? All right, then we're going to start. So if you go down to the pen. Oh, do I even have to say anything about like the textbook or anything? That seems kind of. I mean, you go to the website. That's all I have to say. That kind of explains it. There's a textbook. You'll find it at the website. So I don't have to say it. All right. Okay. So what I'll do today, this is going to be. If you thought that was sort of content free, no. That's what we'll do now. Is I'll start by I'm just going to cover stuff, just broad basics. It's not in any way representative of what the class is going to be like. What I'm going to talk about today. So don't think it is. But it's just we're going to cover the basics, and maybe I'll even get into something that's real. But this is just going to be the very highest level. So we'll talk about mathematical optimization. What is it? The highest level. We'll talk about least squares in linear programming, convex optimization. I'll look at a very simple example, and I'll say a little bit about the course goals and style and all that kind of stuff. Okay, so let's start with this, optimization. And you kind of have to put, depending on the company you're in, you may have to put a qualifier mathematical, because if you say just optimization, if you go to like Wikipedia and type optimization, it goes to something on compiler optimization or something. I mean, who knows what it goes to, or something in business practices. Okay, so if you're in a broad crowd like that, you need to put mathematical in front, just to make it clear. So an optimization problem, I don't have to say that here. I hope. So unless anyone here is interested in compiler optimization, which, by the way, you might be able to do by convex optimization, but no one took me up on that. So okay, so here's what it is. You want to minimize an objective function. You have a variable x with n components, and these are loosely called. This is the optimization variable. Colloquially, you would say that x1 through xn are the variables. By the way, there's other names for these. People would call them decision variables. That's another name for it. And in different contexts, they would have other names. We'll look at some contexts soon. So decision variables is another one, which actually is kind of a nice thing because it tells you these are things you have to decide on, whose values you have to decide. Okay, so you want to minimize an object. You have when you make a choice x, you'll be scored on an objective. That's f0 of x. And we'll choose to minimize that. Now, in fact, you ask what if you wanted to maximize it? Well, then you would just minimize the negative of that function, for example. Okay? And it's convenient to kind of have a canonical form where you minimize instead of maximize. But Okay, and this will be subject to some constraints. In the simplest case, we'll just take a bunch of inequalities. That's fi of x is less than bi. Now, here, without any loss of generality, the bi's could be 0, because I could subtract bi from fi and call that a new fi, and there'd be no harm. This is kind of a nice way to write it because it suggests what really these are. In a lot of cases, these are budgets, for example. It's a budget on power. It often has an interpretation as a budget. Okay? Well, there are other types of constraints. We'll look at it. Okay. Now, what does it mean to be optimal for this problem? By the way, this is redundant. You should really just say an optimal point or the solution. In fact, you shouldn't trust anyone who says optimal solution, because that would be like people who say the following is a true theorem. It's kind of weird. It's redundant. It doesn't hurt logically, but it kind of like, if that's a true theorem, then what about the times when you forgot to add the attribute true? What were those theorems? Anyway, so you see what so this is a bit weird, but so I'd say an optimal point or a solution is a point that satisfies these inequalities here and has smallest value, objective value, among all vectors that satisfy the constraints. That's what you mean by a solution. And of course, you can have everything possible. You can have a problem where there is no solution. You can have a problem where there's one, where there's multiple, and you can have other things, which we'll get to more formally. This is just our first pass. But let's quickly look at examples. So here are some just absolutely classic examples from all over. The first is like portfolio optimization. So in portfolio optimization, here, the decision variables x1 through xn, these might represent the amount you invest in n assets. Okay? For example, if xi is negative, it means you're shorting that asset unless that asset is cash, in which case you're actually you're borrowing money to purchase the others on margin or whatever. Okay, so the x1 through xn is actually a portfolio allocation. Now, you'll have constraints. Obviously, there'll be a budget constraint. That tells you the amount that you have to invest. There might be maximum minimum investment per asset. For example, the minimum could be 0. So you're not allowed to actually purchase a negative quantity of an asset, which would be shorting that asset. So you could have no shorting. You might have a maximum amount you're allowed to invest in any asset. And you might have a minimum return that you expect from this collection, from this portfolio. And your objective might be something like the overall risk or variance in the portfolio. So that would be an example. So you'd say, here's 500 stocks you can invest in. My mean return absolutely must exceed 11%, period. Among all portfolios that meet, and I'm going to have no shorting, and the sum of the xi is going to equal 1, just because I'm going to invest $1. Maybe that's not enough. It's $1 million. Let's say it's $1 million. So I'm investing $1 million. And the question is, among all portfolios that give you that guarantee a mean return of 11%, I want the one with the smallest variance in return. That'd be the one with least risk, for example. And by the way, we'll look at these in horrendous detail later, so I don't have to go over that. But that's the idea. Okay. Next one, I just picked 3 that are just widely separated in style. By the way, this is one where when you solve the optimization problem, it would probably be advisory. In other words, in the sense that you'd look at what came back and you'd say, oh, how interesting that portfolio. Maybe I'll execute the trades to get that portfolio, or maybe not. By the way, this could also be real time. If you do fast, if you're a hedge fund and you're doing fast stuff, this could be program trading. So there's lots of different things this could be used for. Depends on what the time scale is. Is it every 10 seconds, or are we talking a time scale of quarterly? So, okay. Let's look at device sizing in electronic circuits. So here you have a circuit. The variables, for example, might be the device widths and lengths. It could be wire widths and lengths, something like that. And you have constraints. Some of these are manufacturing limits. So, for example, on a current, depending on what fabrication facility is making your circuit, you have a limit on how small the length of a gate in a transistor can be. Okay, so it can't be any smaller than 0.6, 65 nanometers. Okay, that's the smallest it can be. So that's a manufacturing limit there. You would also have, of course, have performance requirements. Performance requirements would be things like timing requirements. You could say, well, this circuit, this thing has to clock at 400 megahertz, for example, or for that matter, 2.8 gigahertz, or something like that. You say that tells you that the delay in the circuit has to be less than some number, because it has to be doing whatever it's doing before the next clock cycle comes up. So that's a timing requirement. And you might have an area requirement. You could say, because if I size it big, I'm going to take up more area, and I could say that no, this portion of the circuit can't be any more than 1 millimeter square. It's 1 square millimeter. So the objective in this case might be power consumption. So you'd say, among all designs that are manufacturable, actually that means something slightly different, but I'll get to that in a bit, that can be manufactured in the sense that they don't laugh when you send, or they don't reject your design instantly, and meet the timing requirements. Among all of those, and the whole point is there will be many, you want the one, or a one, I should say, with least power. So that would be power. That'd be minimized power consumption. Now our last one is just from statistics. In fact, it's a generic estimation model. And generic estimation looks like this. What's interesting here is these are sort of from engineering and from finance and stuff like this. In these cases, the X's are things you're going to do. In this case, they're actually portfolios you're going to hold. And in this case, they will translate into polygons that get sent off to the fabrication facility. Okay? So the XI's are actions. Here, it's very interesting because the XI's are not actions. They're actually parameters that you're estimating. So here, you have a model. For example, doesn't matter, you take any kind of data or something like that. It doesn't even matter what it is. You take some data. And then you'll have parameters in your model. And you want to estimate those parameters. That's what you want to do. And, I mean, that's basic statistics or... anyway, that's our parameter estimation. So you have these parameters. So these are not things you're going to... These XI are not things you're going to do. These are things you're going to... These are numbers you want to estimate. That's what it is. Okay, so you have constraints. So for example, let's say that you're going to estimate a mean and a covariance of something. It can be much more sophisticated, but let's suppose that's the case. Well, we have a constraint here. So here, there might be some constraints. Here's a constraint. The covariance matrix has to be positive semi-definite. Okay, so that's a constraint, because if you created a covariance matrix that wasn't, you'd look pretty silly. So that's just a non-negotiable constraint. But you could also have things like this. You could say, well, you know what? These x's, these parameters here, they must be between this limit and that limit. For example, suppose you're estimating some diffusion coefficient or some parameter. It's known to be positive. Then you should make it positive. We'll get to that later today. These would be parameter limits. Now, the objective is, generally speaking, it depends how you want to describe the problem. If you describe it in an informal way, it's a measure of misfit with the observed data. So, for example, if I choose a bunch of parameters, and then I propagate it through my forward model and find out what I would have had this been the real parameter, the question is, does it fit the observations well? And there's a misfit. Now, another way to say it is it's a measure of, let's see if I can get it right, implausibility. That's really what it is. Okay, so it's a measure of implausibility. And in this case, again, I'm minimizing it. So by the way, in many contexts, you'll see it turned around so it's maximized. So if you're a statistician, for example, someone would say, you would reject the idea of a prior distribution on your parameters. And your objective would be, for example, you'd maximize the likelihood function or the log likelihood function. That's what you'd be maximizing. And that's essentially a statistical measure, in that case of plausibility. You'd minimize the negative log likelihood function, I guess, which I think they call loss in some of these things. Like machine learning, I think don't they negate it and call it loss? Yeah, like hinge loss and all that kind of stuff. Yeah, okay. So, all right. So implausibility, in a Bayesian framework, a measure of implausibility would be something like the negative log posterior probability. So that would be a measure of the implausibility. And of course, if you minimize that, you're actually doing MAP, which is maximum a posteriori probability estimation. Okay, so by the way, if you don't know about we're going to cover all those things again. So this is just very broad brush. If you don't know what these things are, you will. That is, if you take the class. Okay, so Sure. So let's talk about solving optimization. Oh, by the way, so these are examples of optimization. Everyone in their sort of intellectual life goes through a stage. It depends on when it can happen. It can happen in early graduate school, mid-graduate school. It can also happen in a later life, which is bad, like viruses like mumps. It's not good to have when you're an adult. But anyway, so let me describe this stage of intellectual development. Someone tells you you read a couple of books or whatever, and you go like, oh my, you wake up like at 3 in the morning, you're like, oh my God, everything is an optimization problem. I mean, like everything is an optimization problem. It's unbelievable. I mean, like everything is, right? And actually a lot of books start this way. It's really, I mean, they're stupid. I mean, yeah, they start and they say things like, you know, everything is an optimization problem. Okay, well, my answer to that is, I mean, if you have to go through this stage. So that's fine. But just get over it quickly, please. I mean, my response to that is like, duh, of course everything is an optimization problem, right? I mean, so, but the point, what you'll find out quickly is it doesn't mean anything to say that. It's a tautology, right? I mean, it says nothing. What matters is actually what optimization problem it is. Because basically, most optimization problems you can't solve. Now, they don't tell you that if you go take a class in MS&E, for example. They do, but typically they don't tell you this, right? Okay. Or what they do is for full honesty, they do tell you, but they distribute it through the whole quarter. Turns out if you just say a little bit of that message like every day, then at the end of the quarter, no one can accuse you of not having admitted that we don't know how to solve most optimization problems. However, because it was sort of below the threshold of hearing in each lecture, the threshold of notice, I don't know, whatever you call it, it's below the threshold of notice, and as a result, all these students went through, and the big picture didn't come out, which is basically, you know, and the way you cover it up is by going over 57 different types of algorithms for solving things, which basically is a cover-up for the fact that you can't solve anything, roughly. So, anyway, we'll get to that. Okay, let's move on. Okay, so this is related to the following. Solving optimization problem, because to say that everything's an optimization problem is just a stupid tautology. So it all comes down to this. How do you solve them? Well, it turns out solving this general optimization, it's really hard. And basically, in general, I think it's fair to say it just can't be done. I can write down shockingly simple optimization problems, and you can't solve it, and it's very, very likely no one else can. Okay? So, or if you have a background in algorithm complexity, I can write down very innocent-looking optimization problems, and they'll be NP hard. Okay? So, so what do people do about it? Well, there's a couple of ways to do about it.
Question?
Yes?
What do you mean by NP hard?
What do I mean by NP hard?
What does it stand for?
Oh, sorry, non-deterministic polynomial time. Okay?
Okay.
So, so you take at least 2 quarters on this in a computer science class. So I'm going to give you the 15-second version, and people will be, you know, I don't know, rolling their eyes and all that. So I'll tell you about it from a working perspective, what it means. So I think in the 70s, people identified a bunch of problems that so far no one had figured out a good polynomial time algorithm for solving. Okay, polynomial time means. Okay, I'm over 15 seconds now, but I'll do it anyway. Okay, so polynomial time means as an algorithm where the problem comes in, you measure the size, for example, by the number of bits required to describe the. Have you already had all this material? You're shaking your head. Okay, fine. Okay, because then I could be way fast. So you measure by the number of bits required to describe the data, and then you look at the number of operations you have to do, and if you can bound that by a polynomial, then you'd say, well, that's polynomial time. Now, bear in mind, I'm compressing a 10-week course to about 14 seconds. So that means some of the details I'm going to have to gloss over. Okay. So that's that. So there were a bunch of problems where people just didn't, like the famous one would be traveling salesman problem. Okay. And no one had found a polynomial time method. Okay. So someone said, well, I don't know, a guy named Cook maybe, or I don't know the history because anyway. So did the following. He actually cataloged like a whole bunch of problems and said, look, you know what? If you can solve sort of any of these, then if you make a method for solving that, I can make a reduction. I can take your problem and map it to this, and with that I could solve, for example, the traveling salesman problem. Okay? So then you could have an intelligent way of saying 2 problems are just, one is as hard as the other, or one is more hard. Okay. NP hard means, and this is really people are going to cringe if they actually have a background in this. It means it's at least as hard as a whole bunch, a catalog of very hard, of problems thought to be very hard, because there's an asterisk, which I have to give. Okay, so
the traveling is like your prototypical.
that's a prototype. That's your prototype. So basically, and I mean, what I'm saying is actually not true, but as a working definition of what it means, for your purposes, this is going to be fine. It means the problem is at least as hard as, for example, traveling salesman. And let's just leave it that way. Now, let me tell you what that means. By the way, it is not known that these things cannot be solved in polynomial time. That's actually not known. It is thought that that's the case. And it may be at some point somebody will show that you can't solve these. These really are harder. They're merely thought, right now they're thought to be harder. However, I think of it as an insurance policy. Let me tell you why it's an insurance policy. A ton of super smart people have worked on all these problems. And now all of these things are banded together as you would do in insurance. You band them all together. You band a whole bunch of things together. So what would happen is if tomorrow somebody, probably a Russian, proves P equals NP. Okay? So meaning, in fact, you can solve all these problems. Then it means it would indeed be embarrassing for a lot of people. However, the embarrassment is amortized across a huge. You could say, people come to you and say, yeah, you went around and made a big deal about convex their polynomial time, blah blah blah. And I'm like, don't look at me. Look at all the other super smart. I mean, not other. Look at all the other people who, So basically, the embarrassment is spread across a great swath of people. Basically, a lot of people in computer science and stuff like that. And so, it's an insurance policy. But it is thought that they're really hard. But if they're not, you're in very good company with the people who also thought they were hard. Does that make any sense? What?
It's just like in its own kind of field. It's not proved to be certain. It's not like mathematically proved to be a non-polynomial.
That's right. It's just that's why it's still an open conjecture, right? And by the way, it could show up. There'll be some. I mean, if in fact it turns out that these are theoretically not hard, the constant in front could end up being huge or whatever, and that would also blunt the embarrassment. But in any case, the embarrassment is spread across a lot of people. Okay, so that's okay because that's a topic, and we'll come back to that topic several times in the class. But, okay. Okay. So when the methods to solve a general optimization problem, I mean, they always involve a compromise. So if you the two main categories of compromise are as follows. The first one is to not back down on the meaning of solve. Solve means solve. It means find the point that has least objective and satisfies the constraints. That's the definition of solve. So you leave that intact, but you leave open the possibility that the computation time might involve, let's say, thousands of years or something like that. Okay? So that's people call that global optimization often, and it's a big field. By the way, almost entirely it is based on convex optimization. We'll say a little bit about that later in the class. So that's global optimization. Now the other one, which is the one most widely done by people who do optimization, they do the following. It's actually very, very clever what they do. They go and solve. The first time they have solved, they put a little footnote like this. Okay? And then way down at the bottom here, like this, they write this. They write, and now I'll have to ask you to zoom in on that. I'll have to ask you to zoom. Then there we go. And there it is. Okay, so it says not really. Okay, now you can zoom back out again. Okay, so what that means is they make a big story about this, and they say, well, it's a local solution. But what happens is it gets tiresome to say solve locally, local solution, all that kind of, plus it doesn't look good. So what happens is you drop it after a while. And then you say, well, I solved that problem, and I solved this problem. And then the homework exercise say, I solved this. And you go hear people give talks, and they said, so I minimized that. And the point is they didn't. What they did was they got a local solution. But we'll talk more about that as well. Okay. Now there are exceptions. Yes?
Are we going to do any of that? Full non-convex?
Nah. No. But actually, if you were going to do that, I would maintain, although this is not a widely held. Actually, you'll find that many of my opinions are not widely held. but this is among my opinions that are not widely held. This would be another one. If you were going to do that, I would actually do it via convex optimization. and next quarter, which is to say, actually, since we're already like one quarter all messed around, the spring, which I'll probably be giving those lectures, maybe even next week, actually, after I get back from Hong Kong, we could do it. So I would recommend doing it through convex optimization, but that's another story.
But you would be doing it in the spring?
Yeah. Well, now watch out now, because we've crossed new ground. It's scheduled to be in the spring. Who knows when I'll do it? Yeah, we could be early February. We don't know. Okay, so all right. Okay, so what are the exceptions? There are cases where you can solve these problems, no asterisk, nothing. Most famous one in the world by far, least squares, least norm, no asterisk there. It's not like, oh yeah, well, A transpose A inverse A transpose B, or that's it often works super well in practice. It's not, the status of that is the global solution, period. Okay, and there's a couple others that you might not know about. You might though, and that would be things like linear programming problems. We'll get to those quickly, quite quickly. But those are ones where you get the answer, period. No asterisk, nothing. There are actually asterisks in these, but they're much smaller fine print, and I'll get to them later in the class. So don't worry, I will when there's an admission that has to be made, I will make it. I will come clean, maybe quietly, but no, it won't be quiet. Okay, and in fact, the parent of these and a considerable generation is just convex optimization problems. So this is really sort of the exception. So a lot of, I mean, just the rough idea to put it all together is something like this. That most optimization problems you can, so let's review what we've learned so far. We haven't really done anything today, but let's review what we learned so far. A, everything is an optimization problem. Okay, well, that's a tautology. Okay. B, you can't really solve most optimization problems you really can't solve. Okay, so far, great. It's kind of depressing. Now the good news is actually here, that there are huge exceptions. This entire class is about one of the exceptions. So when you do convex optimization, there are no asterisks. It's you solve the problem and there are no apologies, nothing. It's the global solution, which is fun. Is what convex?
Life.
Is life convex? I would have to say no, it's not. I hope it's not.
It's really boring.
Yeah. No, it's not sad. No. If we get to that later today, you'll know why it's not. No. Would you really, to check convexity, you really have to take two instances and then form weighted averages in between, like, for example, the average of two things. What would the average of yours and your life look like? I don't know what. Oh, the other thing that has to happen is that life has to be better than the average of the qualities of your lives. Oh, I don't know. Who knows? I don't know. Well, let's keep that as a running topic that we'll revisit periodically. But for the moment, my position is it's not. No. Is there a question?
Are there other exceptions besides convex optimization?
Yes, there are.
Kind of.
Yeah. All one right now?
Sure.
Singular value decomposition. Okay, so that's one where you can compute the singular value. I can write it out as an optimization problem or something like that pretty easily, right? And well, for example, I could write it out this way. I could say, find me the best rank 2 approximation of this matrix. That's way non-convex, and yet we can solve it, and we get the exact global solution. End of story. By singular values or by principal components analysis, depending on what field you're in. Okay, so that's an example. That's pretty much about it. Now there are some others. There are some combinatorial problems. So if you've taken things on combinatorial algorithms in computer science or something like that, there are combinatorial algorithms on their face would appear to be non-convex. It turns out actually a lot of them are convex. It's quite strange. We'll see that later in the class as well. So you take something that's a combinatorial optimization problem, and on its face would not be. It turns out, though, if you let the variables vary between 0 and 1, you can prove that there's always a solution which is on the vertices. And so there's actually a lot of problems that we can solve. We means, like the whole community, can solve, but are not convex. Some of them actually can be secretly turned into convex problems. But getting a rank 2 approximation of a matrix, excellent example. We can definitely do that and it is definitely not convex. Okay. Any more questions? If not, we'll let's look at some things. So we have least squares, or if you're in statistics, regression. Probably has other. It may have other names. I don't know. So here's the problem. You want to minimize. You want to choose x to minimize the Euclidean norm squared of ax minus b. Well, I mean, if A is full rank or then skinny or whatever, you get an analytical solution, which you know if you know about linear algebra. It's just A transpose A inverse A transpose B. That's actually, in this case, is a unique solution. And in fact, we have a formula for it, which I don't know is overrated. Oh, by the way, I should say something very interesting. In this class, we're gonna look at tons of problems. There will be analytical formulas to almost none of them. So you're going to have to wean yourself away from analytical formulas, actually, which is actually turns out just the sociology of that is very, very interesting, right? Because if you've been trained for 12, 15 years on kind of 19th century math, which was all based on analytical secret formulas and stuff, well, like this one kind of. But we're going to move beyond that. And we're going to find, actually, if you look most deeply into what it means to have an analytical formula, it turns out it doesn't. We're going to look at things like we're going to solve ax minus b with an infinity norm there, or a 1 norm. There's no analytical formula for it now. But it turns out we can calculate that same time it takes you to calculate this. So there's not, having a formula is something you're going to, by the end of this class, I think you'll be less, hopefully, it'll mean less to you.
It's just
none.
So
that's called an unconstrained problem.
So not all optimization problems have that subject to f
right.
less than
yeah. So when we go over this in hideous detail later, that's the case. Oh, I should mention you should be reading, although it seems a bit early since the class hasn't even started. But around the time when the class starts, or I should say, in the year when the class starts and in the quarter when the class starts, you should probably read like chapter 1 and chapter 2.
Right.
And chapter 1 will have a lot of this vague stuff, and then chapter 2 will start in on the real stuff. So, but you're absolutely right. An optimization problem, you don't have to have any constraints, in which case it's called unconstrained, and you don't even have to have an objective. Oh, by the way, if you have neither, that's called the technical name would be a stupid problem, or so. I mean, it's just basically it's minimized. There's no objective says I don't care, and then you say, well, what constraints do I have to satisfy? And you go, it's up to you. So universal solution, x equals 0. There we go. So however, if you don't have an objective, it's called a feasibility problem. Or some people call it, in some fields, they call it a satisfaction problem. So basically, you have a bunch of inequalities, and you want to find a point that satisfies all of them. So that's what that is. So, okay. So all right, back to least squares here. Much more important than the formula, because it turns out you can write down a formula for lots of stuff, and it doesn't do you any good if you actually want to calculate it. So, however, here there are reliable and efficient algorithms, and actually, super high quality, open source, public domain software that will actually carry out this computation for you. So, by the way, that's why least squares is so widely used, because it has computational teeth. It has algorithmic teeth. Instead of just talking about it, which is what a formula would allow you to do, you can actually use it because it has, you can actually compute x star. Okay. Now we're not going to go into too much detail in we're not going to go to too much detail in how you in the numerics. Actually, at one point in the class, we're going to look into this because we're going to talk about how you exploit structure and things like that. And we'll do a quick overview of that. But here, just so you know, the computation time to solve a least squares problem goes like n squared k. N is the number of variables, and that's the small dimension. Okay, k is the number of rows in A. So it's a good thing to know. It's the small squared times the big, as opposed to the small times the big squared. You can do this with, as I said not long ago, in 263. With modern computing, I mean, it's amazing what you can solve. I mean, I think then we worked out, and we just right then and there did a 1,000 variable, couple thousand row least squares problem. Or that's you can call it a regression problem in 2,000 dimensions with 1,000 regressors. And it was like 3 seconds or something, 4, I don't know, something like that. So, okay. Now, by the way, if A is structured, we'll get to that later. If A is like sparse or has special structure, like suppose part of A is like it has an FFT embedded in it. Okay, that would come up in medical imaging. I mean, immediately that would come up in medical imaging. You can do that faster. Okay, or in image processing, you'd have transformations there. These you can solve least squares that are way bigger, least squares problems. Okay. So I would say that least squares is a mature, I would call it a mature technology. Now, when I do this, by the way, people who work on all of this, it's a huge active field in lots of areas. They get extremely angry when I use the word technology. Literally, I mean, people actually are like, they're red if I give a talk, and they come up to me afterwards and they're shaking and they're like, that was totally irresponsible. You should not have called that. You're encouraging people to just use it without knowing what's inside it. That's black box. That's terrible. And I said, well, no, it's good. I said, by the way, I mean this. I mean technology here. Actually, this is the highest praise. This is not an insult. Okay? This is the highest praise. And I say what it means is that other people know enough about the theory, the algorithms, and the implementations are so good and so reliable that the rest of us can just type A\B. That's most of the time. Now, of course, if you're building some real-time system or the sizes get to 1 million or 10 million, you're not going to be using backslash, obviously. But that's a boundary that's growing with time. I mean, that's the wonderful thing about if anything that has to do with computers. Just take a vacation for a year, you know, and my colleagues at the other end of EE who actually do real things, they and all their friends around the world will make stuff like twice as fast. So you just go away and take a vacation. Serious? No, you go to the Greek islands for 3 weeks. You come back. Computers are faster. I mean, so I'm just saying it's great. Yeah. And so I mean, that's the nice thing about it. Everyone's being floated up by Moore's law and so on. So okay. And that's, I mean, certainly the case with all of this. Oh, so what I'll come back to the technology, and I'll say, no, of course, I'm not telling people to just use A\B. Actually, I know everyone in this class has used everyone here has done A\B. Probably only a few actually know what it did. And you look fine, normal, nothing terrible has happened. Isn't that true? No one's, okay. So anyway, what I finally do is when they get real, I'll actually come back to them and I'll say to them, when they're yelling at me, I'll say, hold on, back off here. Do you use TCP/IP? Actually, sometimes, believe it or not, they won't even know what I'm asking. Which is even cooler, right? Because then I'll say, oh, don't tell me you're using TCP. Are you using TCP/IP as a black box? Oh, you don't even know what's inside it? So anyway, finally, some of them will say, okay, yeah, I do, you know. Because like everything is, I mean, even it's stupid. I mean, just if you're even communications on this, on your stupid, you know, on your laptop between different components. And so I'll say, do you know what it does? Most of the time they'll say no. And I say, look, here's what you need to know. You need to know A. Okay. By the way, it is not trivial by any means to make a reliable bit pipe, to transfer bits from one place to another with unreliable medium inside. It is not trivial. That's the first thing. It's no more trivial than it is to solve this problem numerically. Okay? It is not trivial. And I said, all you need to know is this. Very intelligent people have thought about this problem very deeply. They've thought about what can go wrong, deadlocks, all sorts of crazy stuff, and they have come up with algorithms about which they know an incredible amount. That's part one. Part two, other people have implemented them, and as far as you know, and these are very reliable implementations. And the result is that for most of us can just consider certain things to be file transfers to be reliable bit pipes. Okay, we don't have to care about how many packets were retransmitted or how the flow control went and all that kind of stuff. Now, like least squares, if you're doing real-time control or something like that, or ultra, if you're doing some computing that requires extreme reliability, then you know what? You can't treat TCP/IP as a black box. Okay, but so anyway, but you might ask, does this calm them down? The answer is no. This makes them more angry. But anyway, I want to repeat. I mean technology here as in praise of this. Okay. Now, when you use least squares, if you've just come from 263, you've used least squares, okay? But in fact, that's just the beginning. I mean, the way you use least squares is this. It's easy to recognize a least squares problem. I mean, sometimes it comes to you on a platter, like somebody walks up to you and says, oh, I took these measurements. It's a linear measurement model. Help me guess these parameters. I don't, something like that. Or, you know, I received this signal, went through this channel, you know, blah, blah, this kind of thing. Okay. Now, if you learn a few tricks in least squares, boy, you can do well. If you learn how to do weight twiddling and you learn about regularization, basically those two alone, and you are now actually trained. You are ready for, you are ready to do battle with using least squares as a tool. And you will do really well, let me tell you. I mean, so that's, you know. So weights is basically, you know, you go into a problem and someone says, there's no limit on the sum of the squares. You know, the limit is on this, or that's the, then you go, no problem, I have these weights here, and I'll just, you look at the least squares solution, you don't like what you see, you change the weights and you do it again. So, but in, by the way, in engineering we do this all the time. It's called weight twiddling. Slightly derogatory term, but not bad. And I'm sure they do it in statistics and stuff like that, but I haven't got, I don't know that they admit it, right? So, because they like to have this, are you in statistics? Yeah, no, the guy in back, you're smiling. Oh, you are? Oh, good, okay. I like to have, when I'm making fun of a department, I like to have a face to look at. They like to stick to the, you know, so you wouldn't go, if you're doing real statistics, you go back in and like change the prior distribution. Now, admit this, do you do that or not?
I won't be admitting if I'm diplomatic.
That's right. Oh yeah, I have to warn you. The theory behind all of these are being put on. These lectures are being put on the web, so because it's weird and fun and stuff. So don't worry, we'll fuzz out your voice, and if the camera focuses on you, we'll put like the squares. Don't worry about it. If you like, we can obscure your department. So we could beep it out. Actually, would be good. No. All right. So no, he's too diplomatic to say. I know. So I'm just going to guess in statistics, right? They make a big story about like the prior distribution. I bet if they don't like the way that it comes out, they go back and they change that prior distribution. And they cover up their tracks. They don't say that they do this. I'm just guessing. Because I'm like, you know, we do it in engineering, okay? And we're not embarrassed. So I bet they do it. Okay. Next topic is linear programming. So some of you have seen this, maybe. Actually, how many people here, just from the sampling of people here, have seen linear programming somewhere? So a bunch. Okay. MS&E 310? Nope. Somewhere else? In the Greek islands. Okay. Okay. How long was the class? 10 weeks? Yeah, so it's a lot of Moore's Law going down in 10 weeks. So, okay. Okay, so linear programming, I mean, actually, in my opinion, it's what people should learn immediately after least squares, singular value decomposition, linear programming. I mean, if you're going to stop somewhere, that's a very good place. I'm talking about if you want to do, you know, if you actually really want to go out and field algorithms, do real stuff, you know, that's a great place to stop. Everybody should know about it. If you take this class, you're going to know a lot about it. So linear programming is a problem that looks like this. Minimize a linear function subject to a bunch of linear inequalities. Now, we're going to talk about it in horrible detail later in the class, so I'm not going to go into too much detail now. But I just want to talk about the attributes of linear programming. So the first is, in general, except for very special cases, there's no analytical formula for the solution. None. Okay? Just, there is no formula. There's no A transpose A inverse A transpose B. By the way, don't confuse that with our inability. You can say a huge amount of qualitative, intelligent things about a linear program. What you can't do is write down a formula for the solution. Okay? There are reliable and efficient algorithms in software. In fact, in one of your as a homework exercise, you will write actually something kind of in the top class, linear. It'll be 50 lines of MATLAB or Python if you take up our offer on that. And you'll write something that will solve huge linear programs quite well. And it's no asterisk on solve. I mean, you get the solution, period. The computation time, by the way, is proportional to n squared m. Oh, and by the way, that's exactly the same as least squares. Notice that if you equate rows of the least squares objective with constraints. It's identical. That's not an accident, which we'll get to. Yes?
Is there any reason we changed K to M? Just the,
I don't know. Well, yeah. M is a number of constraints here, and K is the height of A.
Okay.
Well, that's the best I can do. I mean, yeah.
Oh.
That's fine. No.
So this M, there's still that many rows in A, right?
Oh, over here?
Yeah.
Yes, if I write that as a matrix inequality, AX less than B, yes, that would be, this M would be that K.
Okay.
Yeah. No, but we carefully, my co-author, Levy Van, we had we spent hours discussing whether it should be M or K, and we finally, you can make either no. It probably should be K.
What about C? What are the dimensions of that?
Oh, C. Okay, X is an Rn.
Okay.
So C is an Rn too. Okay, so, all right. Now, so actually linear programming, by the way, it's a very old topic. Fourier wrote a paper about it. That's a hint. The modern era starts in the 30s, where else but Moscow. But actually the modern era traces back to Stanford. So, and it's George Danzig. And by the way, LP was something that you just talked about until you had computers. At which point LP all of a sudden looked a lot more interesting. That was 1948. So, I think a lot of people, von Neumann also knew about it. A lot of people knew about linear programming. We'll talk more about this when we get there. But I think, something like this coupled with computers, it made a huge, that's a mature technology. Now, linear programming, it looks like it would be easy to recognize. And in fact, in some cases, a problem really has this form. It really comes to you on a platter, like this. So someone comes to you and says, help me solve this problem. I want to minimize this weighted sum of the variables, and I have some budget constraints or whatever. There's about 3 problems or whatever that actually have exactly this form. Okay? But here's the really cool part about linear programming. You will be stunned later in the class when you see the kind of problems that we can reduce to linear programming. It'll just things that do not look like linear programming at all. We will reduce to linear programming, and of course, what that means is they're solved. That's done. So unless your problem is huge, or you have some super real-time thing like you're in communications, right? Then there's a sense in which you're kind of done at that point, right? So I look around and I see, like, if you do medical imaging, that's a mistake because the problems are too big. And then you can't say it's a linear program and kind of walk away. And you can't do communications, at least if it depends on the time scale. You have to adapt the things. Like you can't detect the bits transmitted in a packet because that's coming at you way too fast. So I would recommend that you go into fields that are in between in size. Just for your own. That's for those of you who haven't chosen a field yet. If you've chosen one of those fields already, I'm sorry. But you still have to know this. But, okay. All right. So we're going to see a bunch of tricks. Okay. And now finally I'll say what convex optimization is, because it would seem in a class with that title, one should say what it is in the first lecture. So here's what it is. And we're going to come back, of course, later and go into way more detail. So it's an optimization problem, minimize an objective subject to some constraints. And here's what has to happen. The function f0 and the fi's, they have to be convex. Now, you know what convex is. It means that the graph looks like that. That's a convex function. The graph should have positive curvature, should bend up. Okay? Least squares problem has that form because if I look at the least squares objective and I look at the plot of it, it's a quadratic function squared, and basically it looks like it looks like a bowl. If you take a slice at a level set, you get an ellipsoid. Okay, and so it's convex. Linear programming also is the linear program is also a convex problem because all the objectives are linear. Linear functions are convex. Linear functions are right on the boundary. They have 0 curvature. Okay, so one way to say convex is just positive curvature. So this includes least squares. And actually, kind of the central idea at the highest level behind this class is this. If you want to solve a convex optimization problem, there are no analytical solutions. I mean, of course, there are in special cases, right? We'll see tons of cases, in communications and various other places, where they have special analytical solutions. You've seen one in least squares already. But in general, there isn't an analytical solution. However, they're going to be reliable and efficient algorithms for solving these, and with no asterisk. So you will get the solution. And in fact, from some if someone came from another planet, landed here, and asked you, what you're doing, there would be it would be very difficult to make an argument that solving a convex optimization problem compared to a least squares problem was, for example, that you'd been reduced to a numerical solution, which is what a lot of people might say, with a kind of with a hint of I don't know, kind of they don't like the idea. It's sort of like they say a numerical method in the way that makes you kind of want to go wash your hands or something like that. So it's kind of, I don't share that view. So all right, now the computation time for solving convex problems is roughly proportional to something like n cubed, that's number of variables cubed, n squared m, and f, where f is the cost of evaluating these in their first and second, the functions in their first and second derivatives. We don't have to get into that, but the point is, it's like least squares. I mean, you can basically just solve these, and you will solve them in this class, and you'll know how to write the algorithms that solve them and stuff like that. So it is an exaggeration, in fact, to say it's a technology right now. That's an exaggeration. But, it's not. It's almost a technology, and every time I give this class, it's getting closer and closer. So more and more bits and pieces are basically just as reliable as least squares. Just can be done. Now, I should say something about. I mean, this is actually. We'll get to it later, but this is actually a very profound statement. It's basically saying. It basically identifies a huge class of So let's review what we know so far. A, everything is an optimization problem. Well, we know that's a tautology, so fine. B, we can't solve any optimization problems despite 10 or 20 weeks of lectures on it. Okay? I mean, solve in the sense of get the actual solution. Hang on, I'll get. And now what I'm saying is actually is on the positive side, and it's really cool, and it's not obvious at all. And it says if the objective and the constraints all have positive curvature, then guess what? This thing is just like least squares. You can solve it exactly. You can solve it quickly. You can, and we can ask, although I'm not going to focus on it, you can say a whole lot about it theoretically. We will say some stuff about it theoretically, but that's not going to be the focus of the class.
Just referring to the definition of your convex function, why do a plus b have to equal 1 and a have to be greater than or equal to 0, b greater than
here.
Or alpha beta, rather. Yeah.
Okay, so this is a pedantic way. You might prefer it if I wrote it this way, right? And then 4 theta, but in 0, 1. You might prefer it that way. Do you prefer that?
I don't know why it has to be 0, 1, though.
Oh, you mean...
why can't it be like 99 and 100.5 or negative 5?
Oh, you mean here?
Yeah.
Okay. There are versions where there are different constraints on alpha. For example, if I just say... Now, of course, I totally messed it up. But it said f of alpha x plus beta y is less than or equal to, if it's alpha f of x plus, and there's for all alpha and beta, the function would be called sublinear. So it's a different thing. So
okay.
So there's no. It's because this is the title of the class. This is just a definition of convex.
It doesn't have any physical basis or anything. Like it's not going to turn concave if you suddenly make it more than 1.
No. We'll answer your questions. This is not an accidental, but for now, that's the definition.
Okay.
So that's what it is. Yeah.
Isn't it just a statement of the parameterization of the line between x and y?
Absolutely, that's what it is. It's this picture. By the way, we're going to get to this later, so you're not supposed to be understanding everything. First of all, I'm not saying that much, right? So that's one thing. And then the stuff I am saying is kind of vague. So you're not supposed to be parsing this. You're supposed to. This lecture you're supposed to have your relaxed parsing mode on, and let me get away with stuff and stuff. Well, there'll be a time for, is that really a minus sign or something? That's coming later. So, okay. This is just the broad. The feel of the class. Okay. So actually, using convex so now actually you already know something you didn't know. I mean, it's all very vague and hand wavy, but it basically says optimization problems where the constraints and the objective and constraints have positive curvature. Roughly speaking, we can solve. And by the way, the practical implication of that, the theoretical implication, I think, is extremely interesting. The practical ramifications of this are absolutely immense. Absolutely immense, because it means you're messing on some problem in your own field, and if you get it to a problem of this form, and it won't be obvious. I mean, maybe it is obvious, but then it's not that much fun. It's much cooler when you get to it and you turn things around and you switch some variables around. All the smoke clears. There's some functions there. It's not remotely obvious they're convex. You show they are. And then you're a hero. And it's fun. So, because it actually means a practical thing. It means you can now solve those problems, period. OK. Now, so I go, I give a talk about these things lots of places. People say, wow, that's really cool. How do you learn about this? And I go, well, they say, this is amazing. This is just great. So how do you learn? How do you know if a problem is convex or not? And I go, no problem. You just have to come take my class. You do 10 homeworks, each of which takes 20 hours. And then you do this 24-hour midterm, final. After that, for sure, you'll be quite well trained. And then they're less enthusiastic about it. But OK. So it's actually often difficult to recognize convex problems, and in fact, that's going to be a theme of the class. And I guess I would let me just distinguish a few things there. I would distinguish problems that are sort of that come on a platter, convex, ones where you have to do some work and transform them and stuff like that. And anyway, so let me move on. So I want to do just an example. And just to give a rough idea of what this looks, and for people who did 263, this will kind of tie it to that and it'll give you a rough idea. So here's our problem. I have a surface here with patches, and I have some lamps here, and we're going to choose the illuminating powers in the lamps. Okay, so that's going to be our variable. We'll say that the illumination on a patch here is going to be a sum of the illumination from all the lamps here. And it's going to be the following. It's going to be proportional to the lamp power. And then the proportionality constant is going to be an inverse square law. R is the distance between the patch and the lamp. And there'll be something which is a shading effect. Because obviously, if you're coming in straight on here, then you're going to get the full power. If this lamp, for example, puts very little illumination on here, this one, and if this were below its horizon, if there were a lamp here, it would not illuminate this patch at all. Okay, just this is a simple method, a simple thing. Okay, now the problem is to achieve a desired illumination which is given. So that's I desired. All right, now and you want to do this with bounded lamp power. So I have a maximum power. Powers cannot be negative. That's going to be kind of critical. So powers go between 0 and this, and I care on a log scale because what I care about is missing the lamp power by 2% or 12%. I don't care about absolute. It's actually ratio compared to this one. So the question is, how would you solve it? Well, let's take a look and see how you might solve it. What? I don't. No, you did things like this. Kind of like. I don't think you did this in 263. If your question is, do I shamelessly reuse material from one place and another? I can answer, I can confirm that. Yes. Yeah. Are you asking, have you seen that figure before? The answer could well be, yes, you have. Okay, so let's talk about how to solve it. Well, how would you solve it? Well, the first thing you might do, and by the way, I would recommend this. The first thing you do is you'd say, well, let's just see what happens. Let's try some simple suboptimal schemes. One is just this. You set all the power lamps to the same power, you vary it, and you plot this objective. Okay? You just do a search over it. It's no problem. There's no dishonor in it, right? So you do that. Okay, that might work, might not. That's a good baseline design. Now, you could say, well, I just learned least squares from 263. Indeed, not even just more than a few days ago. Anyway, so you're going to use least squares. So you're going to say, I'm going to do this. You say, look, the objective here is not the sum of the squares. This is real life. This is the illumination engineers. I don't know if there are such a thing, but let's imagine there are. They say, no, everyone uses the absolute value. The sum of the absolute values of the law of the percentage error. I'm making it up, of course, but okay. And you say, yeah, well, good for you. We use sum of squares because I just came from this class where that's what we did. So you solve this problem. Now, when you solve this problem, I guarantee you some of the p's are going to come out negative. But by the way, you're going to do super well. You're going to get a nice flat illumination pattern really nicely, and you'll go, that 263, it was a pain, but I actually did learn something. Then what will happen is you'll look at the powers, and a whole bunch of them will be negative. It turns out you can do really well in illumination with lamps that can spray negative power out. It just turns out you can do that. But so that's not good. So then you say, all right, then the heuristic, then it starts. Okay, so then what do? Here's what you do. You say, if a P is bigger than the maximum power, I just set it equal to P max. If it's a negative lamp, I just set it I turn that lamp off. Okay? And then again, once again, you see how well you did. And you might do better than uniform, maybe worse, I don't know. Okay, now this is what someone trained in least squares would actually do. They'd say, not a problem. They go over here and they say, I want Pj to be in the interval 0 P max over P max. Therefore, I'm going to add a regularization term which charges P for being away from the center of that interval. Everybody see what this is here? You start with all the W's 1, and you solve this problem, okay? And then you just start twiddling, weight twiddling. And by the way, you'll do quite well here. You'd come up with some algorithm that twiddles the weights. And then, how you twiddle them is totally obvious, right? If P comes out outside that interval, that weight needs to go up in the next cycle. If P is because your weight is so high, P is timid and it's sitting at half power because it's going to run up too much of a bill to go otherwise, you want to decrease that weight. And a couple of cycles of this, and you're going to get a very, very good solution. Unfortunately, you might also go on to then write an impossible-to-read 12-page paper with a long pages and pages describing your iteratively reweighted illumination blah, blah, blah thing. Anyway, hopefully you won't, but anyway, all right. You could also use linear programming. If you know about linear programming, you could actually solve this L1 problem where you minimize an L1 norm, and you could say, well, but this is closer than that. And linear programming, it handles the inequalities, the 0 and the P max. No problem. So there's no twiddling there. This would probably do the best of all of them so far. But in fact, the whole thing's silly. The problem is convex. So this objective function, it just looks like this. It's linear over here, and then it's a 1 over, it's an inverse over here. You look at that function, and you realize a couple of things. Well, first of all, the important part, in fact, that's what you're going to be trained on in the next 10 weeks, at least once the quarter starts, is you're looking for convexity. This is what we like to see. By the way, you will see that that function is not differentiable. Definitely not differentiable, okay? So in a lot of other treatments of optimization, differentiability has this very high role because a lot of things are based on gradients and derivatives, and second derivatives, there's no derivative there. Okay? So actually, in convex optimization, differentiability is going to actually play a much lower role. In fact, it's a non-role. This problem, even though it is non-differentiable here, it can be solved as fast as least squares if you know what you're doing. We might even have you write from scratch a solver for it. We could also assign it. It would be 4 lines in a higher level language or something like that to solve this. And that's it. So this is just sort of an example of a problem where, it's not obvious exactly how to solve this, and you can imagine a lot of people not knowing. Let's look at a couple of additional constraints, now that we know that problem is convex. So, yeah.
Where did that curve come from?
I plotted it.
I mean, the equation. Like, how did you know to do max of u 1 over u?
Oh, because that's what, if you go back and if you exponentiate my other objective, you'll find this. And then I did that.
Oh, so you just did it on both sides. Minimize one and minimize the other.
Yes. If you minimize something, it's the same as minimizing the exp of that thing because exp is monotone increasing, right? Okay. Now let's add some additional constraints here. Well, here's one. No more than half of the total power is in any collection of 10 lamps. So that would be one. Another one is no more than half of the lamps are on, but you get to choose which half. Okay. Now I won't go into all the gory details because, for one thing, I'm running out of time. But it's not. Both of these sound complicated or easy or something like that. And if you don't know about convexity, you wouldn't know. The second one is actually unbelievably important. It's unbelievably difficult problem it leads to, right? And in fact, it really leads to you'd have to actually kind of check all n choose n over 2. sets of half the lamps, and for each one solve the problem. I mean, basically everything would come down to that, to actually get the real answer. You could get very good heuristics that would guess an answer, but they would not be certified as the actual correct one. This one, no more than half the total powers in any 10 lamps, that actually is convex, and it's not obvious. But it's something, by week 3 of this class, you will know things like that. And actually, this is kind of cool because these are things that look very similar. I mean, if I said them the right way, I could probably make you think that they are kind of the same question. I'll often do that, by the way, in talks, except I don't give the answer here. And then I pick some poor person, usually someone I know, too, and I force them to add, is it easy or hard if you add these? But the point is, these are just not obvious at all, these things. Okay, yeah. Why what?
Famous? I mean, fundamentally, like historically or something?
Oh, why is it famous? It's not famous.
I mean, people have worked on it, give papers, and have investigated the two problems. One of them is NP-hard, so it should be something about it.
You mean the illumination problem?
Yeah.
I don't know. I think I probably used it like the first. I just made it up one day, like 7 years ago, and then actually John Sitsiklis. I can say this because he's a colleague of mine at MIT. Then the next thing I knew, it was in his book. The famous illumination problem. You've been subjected to it, I believe, in 263. That would be the 263 version of the illumination problem.
Yeah.
Although notice that we didn't ask you to find any powers, because you would have had this annoying problem of the negative powers coming out. So that's selective, though. So I don't think the problem is, it's no more famous than it's been here. So I don't know. Yeah.
You have n and choose n over 2 plus n, choose n over 2 minus 1, and so on. Check.
No, because actually this would subsume all. You have to choose which half of them are actually going to be possibly on, not which are actually on. And it scales like it goes like 2 to the n. It's exponential in n. Okay, so well, let me just say a little bit, and then we'll and then I'll quit. So the course goals and topics are really, I mean, the goal is really to allow you to recognize and formulate problems. You should know enough to actually develop code for these things. It's actually very simple. You'll see it's very simple. You might not think that about 7 weeks into the quarter, but these are really, you'd be shocked at how simple some of these things are, or you will be. And we'll focus a bit on the theory of this. And I think I'll skip this. And I actually do want to just skip forward to something at the very end here, and just say something about a quick history. And I know I'm over, so I'll just take a minute or two to do this. I've already mentioned this. First of all, the theory of convex optimization is more than 100 years old. So the first paper on this is from, I mean, depends how you want to count it, but it's from like 1890, 1895, something like that. But in fact, the ideas trace earlier. By 1970, I mean, it was just kind of very well known, the theory. There's some points here that I think I don't have time to go into, but you can read about this in the first chapter. But actually, what I do want to say is something about why it's interesting now. If this is 100 years old as a mathematical subfield, what makes it interesting now? And what I can say is this: actually, since about 15 years ago, people have been finding applications in lots and lots and lots of areas, and it just sort of starts coming up. It may not particularly help you in some area to know that a problem is convex, but it sure doesn't hurt, and it might actually, in some cases, allow you to solve it. And this was sort of not the case, with the exception of least squares and linear programming. These have been widely used since the 50s, widely applied since the 1950s. But basically since the 1990s, there was a bunch more, a lot of these things were found in areas like machine learning and statistics and control and signal processing and stuff like that. And you get a nice positive feedback loop, because once more people start discovering these problems and start writing papers on, for example, the famous illumination problem, once they start appearing, what happens is people who write the algorithms, they see 2 of these and they go, Dude, somebody should write a super good code for the famous illumination problem. That's what happens. Then they write a beautiful code, well tested, numerically stable, hopefully open source and all that, and then everyone can now solve the famous illumination problem. So, and only then do people realize that there never was such a problem, hopefully. Okay, I quit here, and I'll see you, I guess in theory, in 2 days, but like in 2 months or when, something like that.